Eden comes with a background in physics and electrical engineering, and before Classiq, he used to work at Apple as a signal processing algorithm developer. Amazing. Following his passion for quantum computing, he went to Imperial College London, where he completed a master's in quantum dynamics. In fact, his master's research thesis was developing a quantum algorithm for attacking PQC, that is post-quantum algorithm and post-quantum cryptography. Amazing stuff, Eden. And today, he is here with us to tell you all about advanced quantum algorithms. So take it away, Eden. The stage is yours.
Great. Thank you, Valdan, for this really nice introduction. And I'm really happy and excited to be here. We've been working towards this program for a long time. And I know the Waminium organization and the summer program for several years. So it's a pleasure to be here. So today we are beginning the module of advanced quantum algorithm in practice with Classiq. And I will give first a broad overview of the module, the program that we are going to give in this summer school, and then we'll dive more deep, and then at the end, hands-on implementation of today's session. So in terms of what challenge are we addressing and what are we talking about, we have, on the one hand, we have domain-specific problems, right? So we have problems in condensed matter physics, we have problems in quantum chemistry, we have problems in finance, and many other more areas that quantum computers and quantum algorithms can be applicable for. On the other hand, we have quantum algorithms. So specifically quantum algorithms with some exponential or super polynomial advantage. So there's Grover doesn't give exponential, but we have Shor, and we have QSVT, and we have HHL, and we have phase estimation more general. But what we need more are two things. First, we need more quantum algorithms with exponential advantage or with super polynomial advantage. And then we need more the connection between the domain-specific problems and the quantum algorithms. So the key challenge we are addressing is the development of efficient and useful quantum algorithms. So again, on the one side, we need more quantum algorithms. So these are sometimes pure theoretical algorithms that demonstrate some theoretical advantage. So Shor's algorithm in 1994 was just a paper. And we have, on the other side, the domain-specific problems that we want to solve. So we want to understand what's the ground state energy of some molecules. And then we want to connect the two with quantum algorithms that actually solve these problems. So in this program, we're going to address this key challenge. So by the end of this program, hopefully what you'll gain is a broader understanding of advanced quantum algorithms from a more foundational point of view. So I hope that by the end of this session, you will already start to understand the terms that we are using. So foundational point of view and functionality, and what does it mean advanced quantum algorithms. Another thing that you'll gain is a hands-on implementation of current useful and efficient quantum algorithms. So in a moment, I will touch on what Verdun said. The project that you will do on phase one of the program is to implement by yourself actually one of these state-of-the-art quantum algorithms that demonstrate exponential advantage. So this is very cool. And another thing that you will receive is an initial way of thinking and hands-on capabilities to design novel and useful and efficient quantum algorithms by yourself. So these are the main three things I hope you will gain by completing the program, and the program will include several parts. So at the end, we'll have the project. In the project, you will choose one of three papers, and these are the papers. So classically verifiable quantum advantage from a computational data set. The second one is exponential quantum speedup in simulated coupled classical harmonic oscillator. And the third one is an evidence for quantum utility of the utility of quantum computing before fault tolerance. So these are three very important papers that were published in the last year and a half, maybe 2 years, that demonstrate some quantum advantage or exponential quantum speedup. And what you are going to do in the project is to actually implement these algorithms. So this is quite amazing. There are not so many implementations of these papers, and now people are starting to implement. But in this 1 month that when you're going to work on the project, you actually have the option to implement one of these implementation and maybe to open a new direction or a new research direction within this paper. So to continue upon the work, the foundational work that was done in this paper. So leading up to the project phase, we have the training part. The training will be divided into 2 parts. So in part 1, these are the coming few weeks, we'll have 3 main topics. first we have the Classiq 101, and these are the foundation of the Classiq software and the foundational thinking of how we think about designing quantum algorithm and specifically advanced quantum algorithm. Then we have 2 sessions of quantum primitives. These are the more foundational algorithmic building blocks that we compose these larger algorithms from them. So for example, we have the swap test and linear combination of unitaries and many more quantum primitives that we are going to cover, both from a theoretical point of view, but mainly from a practical implementational point of view. And then in the last session, we have advanced quantum algorithms. So we are mainly going to go over discrete quantum walks, and they're parallel to classical walks, classical random walks. And these will conclude part 1 of the training. So we have 4 sessions, 1.5 hours each session. We have an initial homework, and upon completing the initial homework, you'll receive a fundamental certificate. Now in part 2, these are the next few weeks, and then I think it also overlaps a bit with the beginning of the project. So we have very nice agenda for this. So first we have key papers and researchers' talks. So we know that Rolando Soma, one of the authors of the Exponential Quantum Speedup paper, is going to give a talk about the paper. So this is really, really nice. And then we have 3 other talks from other Classiq members that are going to describe how the implementation of advanced quantum algorithms, so discrete log and Hamiltonian simulation and advanced quantum arithmetics, are made using Classiq, and what are the nuances that we need to have in mind when we design these quantum algorithm in practice, and when we code them, when we synthesize them, when we get an actual implementation of the algorithms that mostly we know from pen and paper and from research papers. So here we have research talks, and we'll have a few, and then we have 3 sessions of 30 minutes each, and we'll have a final homework and an advanced certificate upon completing the final homework. So this is overall the model that we're going to have within this project and the key challenge that we are going to face. Now I have a question for you to get a better feeling about the audience and what your background is. So 3 questions that the moderators of this session are going to ask now in the Discord. So please comment in the Discord. So first, have you heard about linear combination of unitaries? Second, if you have heard about it, so have you ever implemented linear combination of unitaries using some quantum software? And third, have you encountered one of these papers before? So one of the 3 papers that are going to be the topics, the main papers that we are going to address in the project, have you encountered them before? So Vardan, will you be able to share with me the answers?
Sure. Yeah, the polls are going on the Discord chat, and yeah, let's just give them a couple of minutes.
Okay, perfect.
Current status, 1/4 of the people heard about LCUs, 3/4 did not. Having it implemented, around 1/8 has implemented it, or 7 people implemented it, 40 did not. So there will be a great challenge in the upcoming sessions. Have you encountered one of these papers? 20% has, 80% has not. People says no, but I want to learn.
That's great. This is the reason we are here for. Okay, so thank you. And now I have a better understanding of the background of the audience, and that's perfect. So we are going to cover all these in this program. And even if you have heard about it and implemented it, I think it will now give you a new perspective and you will find it very useful. So as Vardan said, I'm Eden, I'm from Classiq. I'm the director of user growth and quantum community here at Classiq. And my background is in physics and electrical engineering. And I did my master's in developing a quantum algorithm for attacking the new cryptographic protocols that are now being implemented or being standardized around the world. So let's start with today's session. So today's session is quantum algorithm development with Classiq, or we can call it the Classiq 101. So we'll go over the foundational stuff of Classiq, and these are both from hands-on and capabilities that you will acquire, and from a way of thinking. So Classiq is also bringing a new way of thinking that now we will start to acquire throughout the program. So by the end of today's session, you'll get a hands-on introduction to a new paradigm in quantum algorithm design, and you'll understand why it is the future of quantum software. So why this is the way we should think about and we should implement new quantum algorithm and quantum software in general. So we'll start with what, why, and how Classiq. Then we'll discuss why functional building blocks and what does it mean. And then we'll start with an hands-on Classiq 101 practice. This is the part that you will actually open the computer and start coding by yourself and going through tutorials and exercises. And then we'll do some hands-on part, and I'll be here to help and to guide you throughout. So what, why, and how Classiq? Let's start with classical algorithm development, right? So now when we think about classical algorithm development or general software that you write or use in everyday life, let's say Python. So we use a high-level language. And this is an example of a very simple algorithm we can call, or just a line of code in Python. So we have an array or a list, and we do some mathematical operation on that list. And we see here like a for loop, and we see arithmetic operations. So we have like a square, and we have subtraction, and we have multiplication. So these are all things that we use in our daily life when we code and we develop algorithm. We don't think about the structure. We have like for loops, and we have the arithmetic operations. One line, very simple, that we actually implement what we want to implement, right? This one line is being translated into low-level languages, for example, an assembly. These low-level languages are the languages that the actual computer, the CPU, the heart of the computer, is being able to process and to execute the operations and the algorithm and the software that we actually want to do. So for example, this is the assembly code that implements this one Python line. And we can see here, for example, one line that said, move the register at this location to this location, and then multiply the register on this location to this location. So we can say move, it's like a swap in quantum algorithm. So we want actually to move the location or the information stored in one register to another one. And then we do a multiplication. So this is one of the foundational operations that are being done at the CPU level or at the very foundational level of the computer. But when we code in the daily life, we don't even think, it's not that we are not only aware, but we don't, most of the times, we are not even thinking about what's going on in the underlying implementation, right? We are only interested in using and utilizing the high-level language that we have in order to perform some computational tasks, some algorithms, some software code that we actually want to implement. And we are not aware of this. On the other hand, nowadays in quantum algorithm development, most of the times we see algorithms, but actually what we see is the circuit implementation. And this is exactly as this assembly code. So this says, take this register or take this bit and move it here or do multiplication. And this is the same as we see here. So this circuit, for example, it implements something. From the circuit diagram, we don't know what it implements, but we see here an Hadamard gate, an Hadamard gate on qubit 0, on qubit 1, a T gate, an X gate, a CMOS gate. So this is the circuit, this is the underlying implementation. This is something that the actual QPU, the quantum computers, can understand. On this circuit, it's the lowest level that we actually implement on the quantum computer, right? So this is a low-level thinking. Building a quantum circuit, it's actually a low-level thinking of the quantum algorithm development. On the other hand, we have high-level thinking, and this is what we really want to do. We want to design a quantum algorithm. So this circuit that we see on the left, it's actually the implementation. This is the low-level, under-the-hood implementation of the algorithm that we design using here 4 lines of code or 5 lines of code with the Classiq language, with the QMod. So here we can see and we can understand and interpret what's going on with the algorithm or with the circuit that implements this algorithm, right? So we see an Hadamard transform on X, some variables, some quantum variables. We do Hadamard transform. So we put it into a superposition. Now, we might not know what is allocate, but basically we initialize this X, this quantum variables with 4 qubits. So we have quantum variables. This is the language, the vocabulary that we use when we speak about the quantum algorithm. So we have an operation. We do the Hadamard transform. This is the one operation on a quantum variable. And then we have another operation with another quantum variable, y, that implements some arithmetic function coherently. So this is an actual simple quantum algorithm that implements coherently on a quantum computer in a superposition, the operation x squared plus 1, where X is initialized to be in a superposition of all possible states with 4 qubits. So it's superposition of 0 and 1 and 2, etc., until 15. And we perform this arithmetic operation in parallel, in a coherent way on all of them. This is the algorithm, and this is the underlying implementation. And what we want to have is this way of thinking of designing the algorithm on the high level. We want to speak and to think of the algorithm with quantum variables, with quantum operations, and how we manipulate these in order to have and to acquire what we want to do from the quantum algorithm. Now, moreover, that we want, and it's beneficial to think on this higher level, and we don't want to be bothered by the underlying implementation. Every quantum algorithm, and sometimes have many, and sometimes infinite number of underlying circuits that implements the same quantum algorithm. So for example, here, we can see 2 quantum circuits. Both of the circuits, they implement the same quantum algorithm. So this same 5 lines of quantum algorithm to have some arithmetic operation. Both circuits, one with 21 qubits and one with 12 qubits, that we can see also that the gates are different, right? The sequence of gates, the circuit gates that implement these are different. Both of them implement the same quantum algorithm. So if we start by thinking about the circuit, first we need to maybe sometimes waste our time in thinking about the implementation itself, rather than thinking about the functionality of the algorithm and letting some compilers, some automated code to come up with the implementation that we want. But moreover, there are many, and sometimes infinite number of circuits, of underlying quantum circuits that implement the same algorithms. And manually, we don't have the ability to go over or to come up with all the circuits implementation for the algorithm that we want and to choose the best circuit implementation for us. And even often we don't know that there are more circuits implementation for the same algorithm that we want to implement. And this is why we need to have this mindset of high-level functional design and design the quantum algorithms and let an automated code, a compiler, a synthesis engine to come up with the underlying implementation that we actually want to have. So this is the way of thinking on classical algorithm development and now quantum algorithm development, and where are we at in today's classical software development, and where we want to be when we design our quantum algorithm with a new way of thinking. So what is Classiq? Classiq is a software platform that enables the design, the optimization, analysis, and execution of quantum algorithms by utilizing the high-level functional design paradigm. So it exactly gives the ability to do what we want to do, right? We want to design to focus on the quantum algorithm on the functional level, to come up with new and novel algorithm, both design them and implement them, quantum algorithm theoretically, and implement them without any domain-specific problem, and then to connect them to domain-specific problem and to actually solve them. And Classiq enables to do that. So with Classiq, there are 2 interfaces. There's one, an IDE, a web-based IDE interface. Just we go to platform.classiq.io, we sign in, and we have all the Classiq platform available over there. And in addition, we have a Python SDK package that accompanies this, and everything that you can do with the IDE, you can do with the Python SDK. And the Python SDK, we just install the Classiq package on Python, and then we import everything that we want to use, and then we can just start write the Python code that actually uses the Classiq platform. We have many researchers and students and enthusiasts from all around the world, from hundreds of universities and thousands of users that already use Classiq for the research, for projects, for education, for many activities that they starting to bring this new paradigm and this new way of thinking to quantum algorithm development and quantum software development in general. So another 2 questions for you. So first, have you heard about Classiq before? And secondly, have you used Classiq before? So just to understand where are we at, and if the audience, if you have background with Classiq, and even if you have background, now we have many new content that will enable you to really master the platform in a new way that you couldn't before. So moderators, if you can please write in the chat.
And the polls are running in the chat. And good news, many of them have heard about Classiq. So about 60% of the audience has already aware of Classiq. How many have used Classiq before? Now that's a ratio is about 20% have already used Classiq. Some of them have used them in some previous hackathons, MIT IQ Hack, in some courses. Yeah, some have used at a Classiq course. So yeah, about 20% have used and about 50%, 60% have already heard about Classiq.
Okay, cool. So that's great. So now you will understand Classiq in a very good way, and you also be able to master the platform throughout this program. And this is up to date, the best program that we've designed, and we invested a lot. So I'm happy for us, and I'm happy for you that you have the option to actually go over it. So that's exciting. Okay, so now let's understand what does it mean to design, to optimize, to analyze, and to execute. So these are maybe new terms. I assume that most of you are familiar with building quantum circuits, right? This is the way you think about when you come and say quantum algorithm or quantum computing from a software perspective. But now we'll try to understand in a more concrete way, what does it mean to design a quantum algorithm and then to optimize it and so on and so forth. So when we design with Classiq, we have a QMod language. QMod, it stands for a quantum modeling language. Now here we can see from the web-based IDE, this is the native syntax of the QMod language. So as we have Python, and we have C++, and we have React, this is another programming language. This is a quantum programming language that you can use. It has its structure, it has its syntax, it has the documentation, the reference manual, and this is the underlying ability to design new quantum algorithm on the high level with Classiq. So QMod captures the core concepts and the core essence of quantum algorithm development. So we developed it using the hundreds and thousands of quantum algorithms, the variations that we have. Very few are with exponential quantum speed, but we have mainly a broad variety of quantum algorithm and variations. So QMod was designed out of these in order to capture all the core concepts, but to build upon them in a way that we can actually scale with quantum algorithm development. So this is the native way to design quantum algorithm with Classiq. In addition, we have the Python SDK package. So as we've seen earlier, we just import from Classiq either all the functions that we want or the specific functions that we want to use. And then we use a decorator. So this effectively says to Python, hey, use this class or this sort of underlying package when you treat the next function. So all the function we use in Python that we want to use this modeling language of Classiq, we use this qfunc decorator. And then we actually write the same Python code that we are used to write. And both of these are equivalent in terms of we can design all the algorithm that we want with the Python package, and we can do with the native QMod language. And as you'll see in later on in this session, every example that we have in our Git repository, in our IDE, and we have plenty in hundreds of examples of tutorials and algorithm. We have them both in the Python SDK and in the native QMod syntax. So when you learn and when you want to explore, you can explore both of them and you can learn both of them. And sometimes it will be more beneficial to work directly with the native syntax and sometimes with the Python package. So this is how we design our quantum algorithm. And this enables this high-level functional design approach, and that is beneficial for quantum algorithm development. Now, why is it good to have this high-level functional design? Because when we design it that way, we can send it to the synthesis engine. So this is the compiler of Classiq. We take the high-level model, and then we synthesize, we compile it into a circuit-level implementation. Now we can insert some constraints and preferences along the way. So for example, we can optimize the algorithm that we want for minimal circuit width or minimal circuit depth. So sometimes we want to use, we have 25 qubits on the QPUs, and then we want to use all the qubits. So we can put maximal width of 25 qubits, and then we want to minimize the depth, right? Because we want the shortest depth in order to apply maybe some error mitigation schemes and so the noise won't completely destroy the algorithm that we want. And sometimes we know, okay, the maximal depth that we are able to use with the quantum computer is 700, let's say, because more than 700 circuit depth, we get completely noise. Up to 700, we might be able to extract some signal out of it. So we can say to the synthesis engine, we can configure that the maximum depth will be 700, and then to optimize over the depth as well, or to say how many qubits that we have that we want to receive the circuit implementation for it. And then we just press synthesis, and we tell the compiler, the synthesis engine of Classiq, take the algorithm that we want. Now with these constraints and these preferences that we want, give me the best circuit that you can come up with. And as we've seen earlier, for two cases, so we had this simple code of y equals x squared plus 1, and we had two circuit implementation that implement the same algorithm. One was with more qubits, but the circuit depth was lower, and the other one was with fewer qubits, but a longer circuit depth. Now, in addition, we can ask the synthesis engine or the compiler to compile for a specific hardware provider or specific hardware connectivity map for a specific basis gated. So on the hand, we have superconducting quantum computers that have a specific limited connectivity map, right? Not all the qubits are connected to all other qubits. And then we can compile the algorithm for this specific connectivity map. On the other hand, we can compile the same algorithm for, let's say, a trapped ion quantum computer that has all-to-all connectivity, maybe with a fewer number of qubits. So we can say to the synthesis engine, what is the backend provider, or what is the backend name, which backend we use, and how we want to compile the quantum algorithm. So this is enabled by first designing the algorithm on a high level, in a high-level way, using QMOD language. If we would start by designing the circuit and not designing the algorithm, so we won't be able to optimize it to maximal depth, to maximal width, to a certain hardware connectivity, and this QMOD design enabling this. So this is optimization of the quantum algorithm. And again, we can do everything also from the Python. So we just code synthesize, and then we synthesize the model that we have created. And again, high-level functional design is a key here. Now, once we receive the circuit implementation, we want to further analyze it, right? So we want to understand if we receive the correct answer. We want to see if we can do some design it in a different way with other functional building blocks, or to understand what was the implementation, right? Maybe we just want to learn or to understand how the compiler of Classiq implements an oracle or a phase kickback or some algorithm. So we can zoom in and zoom out with the visualizer tool, and to understand it on a different hierarchy levels, right? So we can mark what are the quantum variables that we have, and then we zoom in to understand the specific implementation. And then we zoom out to understand on a different hierarchy level. Now, in addition to zooming in and zooming out, we can export the same circuit on different in a different way. So we can export just as a JPEG file, a JPEG picture, and also we can export it as a LaTeX file. So if we're writing an academic paper, for example, and we want to have the circuit diagram, so we can export it directly from Classiq, and this is something that you will do in today's one. Now, finally, once we analyzed it and we optimize and we understood the algorithm, we want to execute. We want to actually run it, maybe on a quantum computer, maybe on a simulator, and to receive the results. So from Classiq, you can do both. So you can have access to almost all the hardware providers available on the cloud. So IBM and Amazon and Azure and IonQ, and we can directly run through Classiq to these quantum computers, or we can use simulator as well. Now, all the results and the jobs that we receive back are being stored in the Classiq platform and are already being interpreted in terms of the variables that we executed, right? So often when we execute the quantum algorithm and receive the results, we receive a long bit string, and then we need to start to interpret this bit string. What does it mean? What are the numbers? What is the notation? Is it small endian, the big endian? And it's not what we actually want. What we actually want is to understand what are the values of the quantum variables that we actually implemented for us. If it's a growth algorithm, we want to understand what solution have we found, right? So this is the search problem. And here we receive the results back in a way that the variables are already interpreted. So we can have also the bit string as well, but the interpretation is what we are looking for. So this covers the first step. So we design, we optimize, we analyze, and then execute quantum algorithm with Classiq, with two interfaces, the IDE and the SDK, and we can go back and forth between the two or use only one of them as most convenient for you. I think maybe it's a good time for question, Vardan, if there are any questions in the chat, and if not, we can continue.
Yes, there are multiple questions in the chat. First, Eros is asking, what is happening in the backend when you are trying to optimize the algorithms? Is it similar to auto routing used in the PCB design?
I'm not sure what is the PCB design, but the idea is from chip design. So I assume this is the term that they refer here. So the idea is coming from classical chip design, right? So initially in the first software revolution, the computing revolution, the transistor was invented, and then there was a boom of computational power that we wanted to exploit, right? And initially, people have designed on the very, very low level, the same as we're doing now with the quantum circuits. So they designed the classical circuits, the classical logic circuits, that actually implemented what they wanted to implement it in terms of the algorithms. And then they understood it's not scalable. So what enabled this computing revolution was one of the things that enabled it after the transistor was this chip design and software automation platforms that enable starting from the algorithm or from the high-level description of what we wanted, and they found the software finds the optimal or maybe the best solution available within the search space of the chip they want to implement. So it's the same logic as in classical chip design. So that's a great question. Okay, so why we need functional building blocks, and this relates to some of the questions that we had. So I've been in the QIP conference. So this is Quantum Information Processing Conference. This is the largest conference, academic conference on quantum computing. And Robin Kothari is from Google Quantum AI, and is one of the authors of the exponential quantum speedup paper that I've shown earlier, and this will be one of the projects. And he gave the tutorials on quantum algorithm development. And this is a slide that I took from his presentation, and I took the picture over there. So he said, and he tried to emphasize this. So he said, try to express the algorithm at a high level in terms of primitives. For example, take the HHA algorithm, and you can decompose it to phase estimation, plus Hamiltonian simulation, plus amplitude amplification. And he suggested and encouraged us to don't count the number of quantum algorithms, focus on the algorithm primitives you learn. And this is exactly coincide with the classic paradigm and the classic way of thinking when we want to give the tools for you, for the quantum software developers, for the quantum algorithm developers, to have the primitives, to have the building blocks, the algorithmic building blocks, first to build them, and then to have them in order to come up and to combine them into a new quantum algorithms. And as I said earlier, one challenge is to come up with new, let's say, theoretical or pure quantum algorithms that we want to have more of these that offer exponential speedup. And the other challenge is to connect them to domain-specific problems that we are interested in. So in quantum chemistry, there is a significant work that was done by Gana Chan that said there is no evidence for exponential speedup in finding, I think, a key problem in quantum chemistry. And this is quite shocking, right? Because when we think about quantum computing and quantum algorithm, we think that for quantum chemistry, this would be the best candidate for solving problems exponentially faster. But until this point, we didn't find, the quantum ecosystem, we didn't find and found a concrete problem in quantum chemistry. And this is the paper, the one of the leading researchers worldwide that said that we didn't find an exponential speed up in concrete problem for quantum chemistry. And this is really, really shocking, right? So we need this new way of thinking, design new quantum algorithm, and find this algorithm to a specific domain, to domain-specific problems. And this will be enabled by thinking on the high level and using these functional building blocks. And these functional building blocks will give you the tool set to come up with new and more efficient and new quantum algorithms. So you should think about these quantum primitives and everything that we are going to do in the coming sessions as enlarging the tool set that you will have in order to come up and to tackle new problems and new algorithms in the future. So let's start with the hands-on part of today's session. So as I shared earlier, we have the Classiq documentation, and this is the best way to start with Classiq. So when you go to docs.classiq.io, this is the screen that you'll see. And we have a few links over there. And this is the place that will enable you navigate throughout the virtual space of Classiq. So first, we have here a link to the Classiq platform, right? You can directly go to platform.classiq.io, but on the top left, you have the link to the platform itself. And obviously, you need to sign up. And if you signed up, you need to sign in whenever you enter, but it's for free and it takes less than 2 minutes. In addition, on the top right, we have a link to our Git library. So we have a large library, a very large collection of many quantum algorithms and applications and tutorials and functions that are implemented using Classiq. And this is a great way to go over and also to contribute. So we want and we encourage the community, we encourage you guys to contribute with new quantum algorithms and new quantum functions and new applications to this library. And we want to be the largest library available for the community to have most state-of-the-art implementations of papers, of algorithms, of application. Everything in our Classiq library is being tested again and again. So everything you have in the library is up to date. And you can just download and run everything from the library. And it's being kept up to date. So even if you upload and you open a pull request and you want to upload a new algorithm that you've designed into the Git library, and then you forget about it, we will make sure to update it again and again and again in order for it to be kept updated. So that's also a great way to understand and to learn, but also to contribute and being part of this Classiq revolution and quantum algorithm development in general for the quantum community ecosystem. In addition, we have the quantum community Slack. So this is the best way to learn more in terms of asking questions and collaborating with other people. And for technical question and technical support, this is the best place to go and to sign in and to ask questions. So we have like the general channel, and you have supporting questions and quantum algorithms. And there are very active and lively discussions over there. So in terms of this program, we will use the Discord for logistic stuff about the program and the model of the Classiq platform. But anything that is technical, or you have question about how to implement something, about the Git library, about how to think about the new algorithm, so it's best to ask it over there in our Slack community channel. All the team of Classiq is available over there, and they answer quite instantly. And also there are more than 5,000 members and users of Classiq that are also active as part of answering. So this is the best way to get technical support and thinking about new things. So the first thing that you'll do in the new documentation is going through the Classiq 101. So this is designed for exactly for people that starting from people that didn't use Classiq at all beforehand, so with registration installation, until being a Classiq expert and being able to design effectively any quantum algorithm available. So it's composed into steps, and it's building up. And the focus of today will be the Classiq concepts part. So these are 7 tutorials divided into the 4 steps of design, optimization, analysis, and execution that we discussed several times. And this is really demonstrating simple quantum algorithms, but in this new way of thinking and new way of designing quantum algorithms. Now, the cool part about this Classiq concept part is that on the top of each page, you have 2 buttons, and that you can view them. One, you can view the algorithm that you view in this page on the GitHub. So this will take you directly to the GitHub, or you can view it in the IDE. So when you press it, after you signed up to the platform, it will open the same example. So this is the Jupyter notebook, but you can create out of this Jupyter notebook the Q mode in the native syntax, and this will be opened in the IDE. So these 2 buttons will help you navigate around the virtual space and to maybe see and go through the tutorial here, and then to open it in the IDE, and then just pressing Synthesize and running it over there. So there are two ways of working, and with the Python and the IDE, and this will enable you transitioning smoothly between the two. In addition, another tool that will help you is that you have on each code cell that has some quantum function, which is decorated by qfont, you have a tab that you can switch between Python and native. So the Python is just the Python code that implements the same, this part of the code, and the native is the same quantum function written in the native qmod syntax. Now, these are very similar, and the syntax, the wording that is used is similar between the two. So allocate and Hadamard transform, it will be the same, but the syntax is slightly different. So this will help you to understand the differences between the two. So you have multiple ways of navigating through these two interfaces. And when you go through the Classiq concepts, I think it's quite beneficial to go between the two. Sometimes it will be easier to work with the Python SDK, for example, for long projects, or you have some pre-processing or post-processing to do. And sometimes if you just want to, let's say, check another quantum primitive or design a new quantum primitive or understand how the quantum primitive is implemented with the circuit, sometimes it would be more beneficial to use directly in the IDE. Maybe it's more quick and straight to the point. So I recommend going through both interfaces when you're going through the hands-on part. Now, what you need to do now, and this is the hands-on part, so to go over the Classiq concept part, and these are the 7 tutorials over there, and you will start now, but then you complete the 5 exercises at home, and you have in Canvas 5 exercises, so I think it's 6.1 to 6.5, and these exercises are linked to one of the tutorials. So almost to every tutorial from the Classiq concept, you have a small exercise. These could be 2-line solutions, but the exercises just want to make sure you really understand what's going on over there and to help you learn in a better way throughout the Classiq concept chapter. So when you read the tutorial, you have some active learning to do by completing one of the exercises. So you'll start now and then you'll finish at home. And then at home, you will need to complete the homework assignment from Canvas. So you can think about it as the concluding assignment for the Classiq concepts and for the basics of Classiq. And I think it's nice. You will need to implement a very rudimentary basic primitive. I don't even to call it primitive, but you will use some constructs of Classiq and you optimize them for different width and depth and different constraints and preferences that you will apply. And then you will use also the visualizer to visualize them, to understand them on different level of hierarchies. And then you will need to explain to us in Classiq, what are the differences in the implementations. So you will do it yourself, and I'm curious to see your results. So we can, I can share like briefly the exercises. So you see, this is the kind of exercises that you have. I will keep this open, and the homework should be something like this. You have everything on Canvas, so you should be able to view all these things. So now I encourage you just to open docs.classiq.io and to go to the Classiq 101. So by pressing on top or here, and then starting going over the Classiq 101. In a few minutes time, I will stop you guys, and then we'll go over the basic tutorial over there to see that we are on the same page, and if you have any questions. And I'm here throughout using the Discord channel for any question that you have. So what exactly we have to do right now? So let me share the screen again. So right now we should go over so first go to the docs.classiq.io and start going through the Classiq 101. And by the end of the session, I hope you'll finish going through the Classiq concepts part. And then for each, or almost for each tutorial over here in the Classiq concept part, you have an exercise that is available on Canvas, and I can share the screen as well, that you can see all the exercises. And the idea is that you just go over it and try to understand it in the best way you can, and then the exercise just verify that you really understood it. So what you need to do now is to go through registration installation, running the hello world example, making sure that you have everything installed and you can work with it, and then go through the Classiq concepts tutorials and complete the exercises. Okay, what's the best way to go over Classiq documentation? That's a great question. So on the high level, there is one page of what's Classiq, and you can go through it. It's effectively what we've discussed in the presentation, but you can also go over it. Next, you have the Classiq 101. So this is what you're going to do today. You have the Classiq concepts. This is the main part of the Classiq 101 that you'll need to cover. And then you have one example of a quantum primitive. So it's the phase kickback. You can view it. And then you have the what's next. And what's next, you have several options. So one, there's the explore. So this is the world that you just explore quantum algorithms by yourself. So you can go to the Classiq Git library, and every algorithm and every software that is in the Classiq Git library is also available here in the explore page. So let's say algorithm, and we can view the discrete logarithm. So this is a tutorial of the discrete logarithm. Now we can view the tutorial on our GitHub repository, and we can download it from here and to see the history. And we can also experiment in the IDE. So we can open the same example in the IDE and view this is the same code, the same QMod that is given also here and is given also here. So all are the same, and you have several interfaces to work with. And so this is the Explorer. And then you have also, you can do by yourself, but you'll have it as assignments in the next modules, in the next session. So you have some practice material, some workshops or tutorials that you need to complete, some exercises in between. So you can also do that. And there is within the reference manual, the platform, and specifically QMod. This is a great way of learning or using it as a dictionary of the platform. So this is sort of the reference manual or the API documentation. When you're designing the algorithm and you have a question about the syntax or you don't know how to do something, this is the place to go. Now I'm in the Classiq platform. So this is the homepage that we have. And then we have here the model tab. So all the models are being stored in the model tab. And this is the first page or the first place we'll start by designing a new algorithm. So we can go to tutorials and to the Classiq concepts. And let's say we're going to the design, the QMod language. So this is the first example. This is the example we also covered in the slides. Now we can synthesize it. So we're pressing synthesize. And now it's sent to the Classiq backend, and we receive back the algorithm itself. Now, on the high level, we receive only one block. But here we have a plus button that enables us to zoom in and zoom out according to the implementation of the algorithm, right? So here we have Hadamard transform. This is the first step of the algorithm. So we can understand the circuit in terms of the algorithm and the functionality of the algorithm. And now we can zoom in and see the Hadamard transform is just a sequence of Hadamards applied on all the qubits. Now we have here the arithmetic operation. And so here we can see this is the X variable that is the argument of the arithmetic operation. And this is the expression result. So this will refer to Y. So we can change the name here to Y. And we can zoom in and understand how this is made. So it's made of power and adder, right? So the algorithm we wanted to implement is x squared plus 1. So first we need to do the power, the x squared, and this is the implementation itself. So if we would need to start from the implementation of x squared, it would be very difficult. I don't know by heart the implementation of x squared, but I know what I want to achieve, and I know that Classiq or the synthesis engine can do that for me. So this is the implementation, and then we can also learn how to implement a power. So this is a quantum circuit implementation for the algorithm x squared. Now we have the adder. So we add, it's used the QFT adder. So this is one implementation of the adder. So we can zoom in and zoom out to the different hierarchy levels in order to understand the underlying implementation. Maybe on the qubit level, but also on the register level, so with a bunch of several qubits, and on higher hierarchy levels. And the plus sign got it, great. It's working for me, great. So if I'm going back, so in the Classiq 101, we have the registration installation, then we have the hello many words. So as I said several times, in Classiq, we have several words that we are working with. So we have the IDE world, and we have the Python SDK world, and there are ways to go back and forth between them. So the first world is all in IDE, and you can just copy and paste it in the model tab, and then there is a sequence of GIFs that will guide you through. But there are several other ways to go through it. So you have in which platform you're doing every step. So you can design in the Python SDK and optimize in Python SDK, and the only thing that is used only in the IDE is the analysis. So the circuit and viewing on different hierarchy levels, this is only done with the IDE, but everything else you can do both in the SDK and in the IDE. Now you can go through this, and then it will cover all the things and the hello world example on these different world combination between the IDE and the SDK. And once you finish with the hello world example, so you're encouraged to go through the Classiq concepts. So this is a deep dive into the 4 steps of design and optimize and analyze and execute. I think the newest part here is the design phase. So designing the quantum algorithm and the qubit language. And in a few minutes until the end of the session, I will roughly go over this example and dive into more detail. But I really encourage you just to go over it, to think about it for a second, and then to complete the exercises, because active learning, I think it's the best way of learning, and trying to tweak and change it throughout. So right now you should go over the exercises, and then you should finish this at home. So for the end of the session, I want to go over the qubit language tutorial. So this is the first tutorial that you will encounter in this Classiq concept page. And the concrete example that we are going to do here is to calculate x squared plus 1. So this is the task that we are given in this tutorial. So again, to coherently calculate y equals x squared plus 1. So we initialize first x as a superposition of all the numbers between 0 and 7. And then we calculate the arithmetic operation of y equals x squared plus 1. I see that there is a typo. No, it's not a typo. This is what it should be. And again, I think maybe the new way of thinking is that we think about now quantum variables just as numbers that we put in a superposition. So we don't think about them as the underlying bit representation or qubit representation. We think about x as a superposition of different numbers, and then we apply some quantum algorithm or some arithmetic operation on it. So the code that actually implement this is these 5 lines. And so we first import all the functions that we want. We can also import everything. So if we import the asterisk, we can import everything, and then we design the algorithm. So first, in the Python version, we can see a decorator of qfunc. This means that in Python, this is the way we write a quantum algorithm with q. And then we have this main function. So we will always have a main function. This will be the heart of the algorithm that we design. And from it, we will maybe call to other functions, but maybe we'll just use all the functions within this, or all the building blocks within this main function. Now, first we have allocate. So we initialize the quantum number, x. So next you will understand what is a quantum number, but effectively it's a variable that is representing some number or some arithmetic. So here the x is a quantum number because it stores a superposition of the numbers between 0 and 7, including. So we allocate is equivalent to initialize. So we initialize the quantum variable, which is of type QNUM, with 4 qubits. And then we apply the Hadamard transform on x. So the Hadamard transform creates a uniform superposition of all possible states. So when we initialize x, we just tell the qmod language or tell the compiler, okay, this is a quantum number that we want to have. So we initialize it, and effectively it receives the value of 0 when it is initialized, but it mainly says, okay, we now starting to use this quantum variable. Now we apply this Hadamard transform to put it in superposition. And then the heart of the algorithm, or the heart of the code here, if we can call it the algorithm, is to apply y equals x squared plus 1. The only difference between what we are used to with classical computing is that we have this sign for equal, because we cannot overwrite the equals of Python. In the native syntax, we can see it's almost the same, but in the native syntax, we have just y equals x squared plus 1. So because this is the native syntax in qmod, you can just write it as it would be quite intuitively. So this is the first algorithm, or the first part of code that you can see with Classiq. Now, here we already see some of the powers of Classiq, right? We actually implement some arithmetic operation, which is not so simple to implement, with one line of code. And we are not thinking about the implementation itself. And it's not that there is only one implementation. So it's not an aggregation of a sequence of gates that implement this. There might be many different implementations. For example, the adder, there are two well-known implementations for a quantum adder. So a ripple carry adder and a quantum Fourier transform adder. So the synthesis engine, the optimizer, chooses the best implementation for the adder that it seems to be for this case. In this case, we synthesize. So after we design the algorithm, we synthesize it. So from the Python, we do the create model from main. So from the main function, we create the qmod, we create the underlying model representation. And then with the synthesize command, we send it to the synthesis engine. So we send it to the backend of Classiq to receive back the quantum program. So this is a pure Pythonic function that is used for this. Now, the equivalent of these 3 lines of code in the IDE is just pressing the synthesis button, as we see. So this is the synthesis here, and then we are transitioned into the quantum program visualize page. Now, this is the simple example. On the bottom, we can see the key qmod principles. So here we aggregated 5 qmod principles that will accompany you throughout the journey of designing quantum algorithm with Classiq, and hopefully for life now. And these are like key things that you should follow, more technical things, but they encapsulate the core understanding and the core value proposition of the qmod language, or of high-level programming languages and qmod language in general. And let's go over them quite briefly, but then I encourage you to go over more deeply. So there must be a qfunc decorator in Python, or a keyword in the native syntax, right? So in every function that we use with qmod, so in a Python, we use this decorator qfunc, and with the native syntax, we just use the keyword qfunc before any function that we are using. And if you're not familiar with decorator, that's fine. You can just work with it and say every function that I'm using some quantum things, I'm putting this line before, or you can just check out in Google, and I think there are good explanations over the web about the decorators, but you don't need to master this. You can just use it as it is. Now, the second thing is that there must be a main function. So as we see here, this is the main function. We could use more functions, and in other tutorials, we'll use more functions. But always there will be a main function. From the main function, we create the quantum model. So the keyword, the actual word main should appear on every quantum algorithm that you design. Then the arguments of the main function must be declared as outputs. So this is a subtle point. So we see here that we initialize or we declare the quantum variable that we name it x, and the type of this quantum variable is a qnum. And then in the next tutorial, we'll dive into what are quantum variables and what is a qnum. But here we can already understand the type is qnum, and this is an output. So we just need to use this keyword. The logic behind this is that it says that the quantum variable x is initialized within the scope of the function. So this is a subtle point that I think throughout the Classiq 101 you will understand better. But the idea is that if you initialize a quantum variable within the scope of a function, so here we can see we initialize or we allocate within the scope of the function. So we need to use the output declaration on when we declare the variable. This is always true for the main function, and for the other function, as we'll see, there are some cases that we'll use it and some cases that we won't use it. Every quantum variable needs to be declared before it is used. So we need, before we use a quantum variable, we need to declare it. Now we can declare it either as arguments of the function, or there are other ways to declare it, but we can see that we have some declaration that says, okay, dear QMod compiler, we have here the X variable. This is of type QNum. We have here the Y variable. This is of type QNum. So we declared it, and only then we used it and we applied some manipulation on it. And also, after we declared it, we initialize it, right? So X is initialized with the allocate operation, and Y is initialized with the arithmetic operation. Maybe it's hard for the beginning, but these are 5 key QMod principles that we need to follow when we design with quantum, with the QMod language, when we design quantum algorithms. Now, the rest of the tutorials here in the design section will dive into more details about what are these constructs and variables and operations that we use here in this short example. So I encourage you to go over it, and alongside this, to actually do some hands-on example and the exercises that you have on campus.
And then